All right, today in Algebra 2, we are going to finish up section 6.4. So we're going to go to the back of the notes where it talks about inverses of exponential and logarithmic functions. So it wants me to write the equation of the inverse of the function. Okay? So I'm just going to list over here our steps. So step number 1, we will write in y equals f of x form. So we will write y equals f of x form. Step number 2, then, we will switch x and y. So remember, that's what inverse means, trade places with x and y. Step number 3, we will write in log form. This is the directions for number 1 because it's starting out as an exponential. So this is how, if we have the exponential, how we find the inverse. After we write in log form, we will solve for y. And then finally, write as inverse. So this is when you start with exponential. So exponential to the inverse, which is a log. So number 1 says f of x equals 10 to the x plus 1 power. So the very first thing we're going to do, we're going to take it, instead of f of x, we're going to make it say y equals 10 to the x plus 1. Now we're trying to find the inverse, so inverse means trade places with x and y. So switch places with x and y and make this say x equals 10 to the y plus 1. So now I want to solve for y, but since y is an exponent, I need to take the log of both sides. So I'm going to say log of x equals log 10 to the y plus 1. So on this side I have log x equals, now over here, log of 10, remember log base 10 of 10, that's just 1, so that all goes away and I'm just left with y plus 1. Now all I have to do is subtract 1 from both sides. So I get y equals log x, all of that minus 1. So now all I have to do is write with the inverse. So trade my y to inverse. So f inverse of x equals log of x, all of that minus 1. There's the inverse of that exponential. Okay. So now number 2, write the equation of the inverse. G of x equals log base 7 of x plus 5. This is a logarithm. So if I'm going from a log, I want the inverse. It's going to be an exponential. Our steps. Again, we always start out step number 1. We write y equals f of x form. So we get rid of the f of x. Step number 2, we always switch x and y. Step number 3, since it's now a logarithm and I'm changing it to the inverse, which is an exponential, I write it in exponential form. Write in exponential. And then solve for y. And write as f inverse of x. Okay. All right, so number 2, g of x equals log base 7 of x plus 5. So I'm going to make this say y equals log base 7 of x plus 5. Now I'm going to change places with x and y. X equals log base 7 y plus 5. Write the exponential, so 7 to the x power equals y plus 5. Solve for y, so I get y equals 7 to the x minus 5. Change my y to f inverse. 7 to the x power, all of that minus 5, is the inverse of log base 7 x plus 5. Okay, so number 3, f of x equals 3 to the x plus 2 power. So the very first thing I'm going to do, make this say y equals 3 to the x plus 2. I want to find the inverse, so I trade places with x and y. X equals 3y to the plus 2. Log of both sides. So log x equals log 3 y plus 2. Now we haven't talked about our properties of logarithms yet. Okay? So instead of saying the log of both sides, what we can do here is just write this as a logarithm. Instead of taking the log of both sides, we can change this to a logarithmic function. So if I change an exponential to a logarithm, remember this is going to say log base 3 of x equals y plus 2. So now I want to solve this, get y by itself. All I have to do is subtract 2 from both sides. So I get y equals log base 3 of x, all of that minus 2. Put my inverse. So log base 3 of x minus 2. So if I don't have a 10, then I just rewrite the exponential as a logarithm, right? Instead of putting the log on both sides and expecting my log base 10 to cancel. Let's look at number 4. G of x equals log base 7 of x minus 2. Make this say y equals log base 7 x minus 2. Trade places with x and y. Change to an exponential, so I get 7 to the x equals y minus 2. Get y by itself, so y equals 7 to the x power plus 2. Make it say f inverse equals 7 to the x plus 2. There's our inverse. Right? The last thing that we want to look at with the inverse is interpreting the inverse. Right? It's the last page of notes. Interpret the inverse of a formula involving logarithms. So it tells me a company uses this function to relate sales revenue R and advertising cost A. R equals log of A plus 1, all of that plus 25. So first it says, what is the equation of the inverse formula? And then which equation would be easier to find the value of A for a particular value of R? So first let's just find the inverse. So if we want to find the inverse, we need to get the logarithm by itself. So if I want to get the logarithm by itself, I'm going to move the 25 over. So I'm going to make this say r minus 25 equals 12 log a plus 1. Now I'm going to divide everything by 12. So I get r minus 25 divided by 12 equals log of a plus 1. I'm going to change it to an exponential. So I have 10 to the r minus 25 divided by 12 power equals a plus 1. Solve for a. So I get a equals 10 to the r minus 25 divided by 12, all of that minus 1. So this is my inverse. So it started out as a logarithm. I changed it to an inverse. I changed it to an exponential to get the inverse. So now it says which equation would be easier to find the value of A if I'm given R. So if I'm given the R value and I have to find the A, the original equation, that would be difficult. The inverse, if I'm given R and I want to find A, that would be much easier. So the inverse would be easier to find A given R because the inverse is solved for A already. Number 2 says describe what happens to the amount of monthly revenue as the cost of advertising increases. How might you determine the optimal advertising budget and explain? Okay. So R equals 12 log of A plus 1, all of that plus 25. That is our monthly revenue. This is a logarithm, right? So it's asking me what happens to the monthly revenue as the cost of advertising increases. My base here of this log, so the base of my log is a whole number. Therefore, as x approaches infinity, y approaches infinity. So they're both increasing together. Therefore, as monthly revenue increases, cost of advertising increases. Okay, so they're both going to increase together. So then it says, how might you determine the optimal advertising budget? Okay. Well, in order to do that, we would determine what our revenue goal is. So determine what our revenue goal is. And plug it in to find the advertising cost. So determine what our optimal revenue goal is, and just plug that into that equation, to the inverse equation to figure out what is the advertising budget. Last thing we want to look at, we're going to compare two logarithmic functions. So number one, it says logarithmic functions can approximate the altitude of a plane over time. Which plane's altitude shows the greater rate of change over the interval t between 10 and 15? Rate of change. Remember, that's the same thing as saying slope, right? That's the same thing as like our slope, average rate of change, right? So rate of change, so plane A, rate of change. Over that interval, what we want to do, remember our formula, we will find the altitude A of 15 minus A of 10 over 15 minus 10, right? Because this is y2 minus y1 over x2 minus x1. So plane A, this is the equation that they give to me. If I plug 15 in here, so 9,200 times the natural log of 15 plus 10,000, I get 34,914 minus, now I'm going to plug 10 in for t, 9,200 times the natural log of 10, all of that plus 10,000, and I get 31,184. Divide that by 15 minus 10, or 5. So this is 3,730 divided by 5. Divide 3,730 by 5, and we get 746. Let's see, we are feet per minute. So feet per minute. So the average rate of change of plane A is 746 feet per minute. That's its altitude. So now plane B, switch colors here. We're going to do the same thing for plane B. Plane B, though, look how nice they've given me these points already. So plane B, I'm going to say 39,449. So y2 minus y1, 37,497 over 15 minus 10. So I'm just plugging in y2 minus y1, x2 minus x1. On top, this is going to equal 1,952 divided by 5. When I divide that out, I get 390 feet per minute. So the average rate of change of plane B's altitude is 390 feet per minute. So it says which plane's altitude shows the greater rate of change? Plane A, right? Plane A has the greater rate of change. Between 10 and 15 minutes. Is plane A, 746 feet per minute. So number 2, it says, for which plane do you think the altitude will change more quickly over the interval 15 to 20? And explain your reasoning. These were both logarithmic functions, right? So they both follow a logarithmic model. Therefore, plane A will continue to increase at a greater rate. All right, so that is section 6.4. That wraps it up. Your homework will be the Envision 6.4 worksheet, numbers 19 through 26, 28, and 29.